Today, on how it's made. Pharmaceutical blister packs. Deli slicers. Oysters. And Weathervanes. While the pill bottle isn't yet passé, we're seeing many medications being sold in blister packs, those cards on which each pill is lined up in a row and encased in a packaging bubble. To take your medication, you simply press the blister and push out the pill through the breakable backing. Blister packaging prevents moisture and air from coming into contact with the medicine. The package is comprised of 2 layers, typically an aluminum foil sheet called the lidding and a PVC plastic sheet with rows of blisters. Once the manufacturer designs the packaging format, the engineering department tailor-makes the tools to produce it. This computer-guided mill creates the die which will form the blisters in the PVC sheet. They mount the die on a machine called a thermoformer. As the PVC sheet enters the machine, an oven heats it up, making it soft and malleable. The die then strikes it, imprinting the pattern of circles. A split second after the forming station closes, a blast of air forms the circles into raised blisters. Refrigerated plates then sandwich the sheet, setting the new shape. The pills arrive at the packaging facility in bulk containers. Workers sift off any pill dust that may have formed, give the pills a preliminary inspection, then load them into a large hopper. If they were shipped with any moisture absorption packets, an employee now removes and discards them. The hopper feeds the packaging machine. The blister sheets move through open side up so that the pills fall right in. Rotating brushes and paddles disperse the pills onto the passing cavities, which are designed to fit no more than 1 pill per blister. An inspector fills any empty blisters, while a sophisticated vision system detects any broken or chipped pills, flagging them to be rejected later. The blisters enter a seal station, where they're mated with the foil lidding. One side of that lidding is printed beforehand with product information. To make the printing plate, technicians mount a blank rubber mat on a cylinder. As the cylinder revolves, a powerful laser cuts away at the rubber until the information to be printed appears in raised lettering, just like a traditional rubber stamp. They transfer this rubber plate to the packaging line's printing station, where the rubber plate picks up ink and rolls it onto the lidding. The ink dries by the time the lidding reaches the sealing station, where lidding and blister sheet meet. The next station simultaneously applies pressure and heat. This activates an adhesive on the lidding, heat sealing the sheets together. Then refrigerated plates cool the surfaces to set the adhesive. Here, a die punches the hole through which the blister pack will lock into a childproof case. Then another die punches the individual blister packs apart. Vacuum arms transfer the packs to a single-file conveyor belt, dropping any packs which the vision system identified for rejection. This automated arm sets childproof cases on a track moving in parallel to the conveyor that holds the blister packs. Then a loading arm slides a blister pack into each plastic case, mating the hole in the pack to the case's internal lock. Finally, an applicator places an adhesive label bearing all the required identification and safety information onto each passing case. Random samples undergo a series of quality control checks. In this test for water and air tightness, technicians submerge the blister pack in blue dye and apply a vacuum. Any dye penetrating the pack would indicate a hole in a blister or a flaw in the seal between the plastic and lidding. Should a particular medication require extra protection, the blister pack can, for example, be made of light-resistant materials or contain an extra moisture barrier. Invented in Holland in 1898, the Deli slicer launched a revolution behind the meat counter. No longer was it necessary to carve meats and cheeses entirely by hand. With the turn of a crank, the Deli slicer produced precise cuts in a jiffy. The modern deli slicer is powered by electricity, with a manual override for the carriage which delivers food to a spinning blade. Production begins with the cast aluminum base. A worker installs a cam mechanism which is part of a system for adjusting the thickness of the slice. He threads wiring connected to an on-off indicator light through holes in the base. Then he screws an index knob onto the shaft protruding from the cam mechanism installed earlier. An important warning label comes next. Then he seals the gap around the blade shaft with silicone and removes the excess with soapy water. Next up is the wiring for the slicer motor. She clamps the wires together and bolts the clamps to the inside of the aluminum base. She inserts the on-off switch in the plastic trim, then attaches a device that will slide to adjust the gap between the gauge plate and the blade, thereby controlling the thickness of the cut. The deli slicer is ready for the slide rod and carriage subassembly, which will deliver food to the spinning blade. The carriage will move across a track, which she now attaches to the lip of the base. She tests the carriage assembly to confirm that it's on track. The next worker secures the blade motor to the wiring with bolts. He connects the motor to the blade shaft with a drive belt. Operating the motor allows him to observe the drive belt and pulleys in action, confirming that they operate smoothly. Once the gauge plate is installed, they move on to making the blade. Computer-guided cutters slope the steel surface and carve a precise bevel onto the rim. It goes from a rough blank to a precisely shaped blade in just minutes. The next worker etches the company logo and production date into the blade metal. Another lathe pre-sharpens the blade to the point where it could cut through something as fine as 0.004 of a centimeter. A worker slides the blade onto the drive shaft and secures it in place with a nut. He now checks the alignment of the gauge plate in relation to the blade. He turns the thickness mechanism to close the gap and checks it again. With the dial indicator, he measures the position of the blade even more precisely. This tool confirms that the blade is in the exact position for cutting and that it won't lose that position once activated. This deli slicer comes with its own sharpening system, a grinding wheel in protective casing. He mounts the grinder and activates it to hone the edge to razor sharpness. When the blade cuts through tissue paper cleanly, it's ready for real slicing action. A worker screws the arm for the sliding tray to the carriage. He uses a spacer disc to establish the correct distance between the food tray and the blade. He sets the food tray on the arm and checks the gap between it and the blade. Once the two are correctly aligned, he removes the spacer and latches the safety guard to the blade. Now for a test, verifying that the tray doesn't drag or scrape against the blade guard. Below, they've installed rods to move the carriage on the track. The system can be manually operated or driven by a second motor. Finally, a worker cleans this slicing machine until it gleams. At 61 kilograms, this deli slicer is no lightweight, so they use a crane to lower it into the packing box. Hefty and heavy-duty, this deli slicer should have what it takes to cut it at the meat market. Oysters are versatile shellfish. You can bake them, boil them, smoke them, or eat them raw right from the shell. Over the years, wild oyster stocks have declined due to overfishing and pollution. So today, 95% of the oysters we consume come from oyster farms. Oysters are filter feeders, meaning they draw seawater over their gills to trap and eat the phytoplankton, microscopic aquatic organisms. An adult oyster can filter up to 5 liters of seawater per hour. Oyster farms are located in or by the sea because the oysters need to feed off seawater to survive. The hatchery keeps the oysters in upwellers, mesh-bottomed buckets sitting in seawater. Oysters can reproduce once they're 6 months old. However, the ideal breeding age is between 2 and 10 years. At breeding time, workers put the oysters into breeding trays, oscillating the water temperature between 20 and 30 degrees to stimulate spawning. The females squirt out eggs, the males squirt out semen, and 16 hours later, the fertilized eggs hatch larvae. Right from birth, the oysters feed on a blend of the phytoplankton they'd eat in the wild. The hatchery dilutes this plankton mix in seawater and pumps it to the oyster containers. Marine biologists manage the ponds in which the hatchery grows its phytoplankton supply. The larvae are so tiny you can't see them in the water. They're visible only under a microscope. Right from the time they hatch, they already have a shell and can swim. By about the 2-week mark, they've grown to the size of a speck, about 1/3 of a millimeter long. However, now they act like miniature adults and stay put. The hatchery keeps them in suspension in circulating water, so they have an ample supply of food and oxygen. As they grow, they're transferred to progressively larger bottles. By the time they're 4 to 6 weeks old, they're ready to leave the hatchery and move to the oyster farm. The farm floats in a harbor. The baby oysters arriving are at least a millimeter long. They go into upwellers. Pipes circulate seawater, and the babies filter feed on the natural phytoplankton. Over the next 6 weeks or so, they quadruple in size, to about 4 millimeters in length. Workers then pack them in plastic mesh bags, stack the bags on metal racks, and suspend the racks in the sea. The oysters live like that for 3 months, getting transferred into progressively larger mesh bags as they grow. Halfway into it, the oysters are this big, about 20 millimeters long. By the end of the 3 months, they're double this size, grown up enough to leave home and venture out into the real world. Workers lay them on the seafloor and leave them for 6 months to reach harvest size, which is determined not by length anymore, but by weight, 80 grams. To finally harvest the oysters, they lower a custom-built machine that's part dredger, part conveyor. It generates jets of water which blow the oysters off the seabed onto the conveyor. They travel up, out of the water, into the boat. That conveyor dumps the oysters onto another conveyor, which leads to the picking station. There, workers select the correct size oysters and put them into baskets. Whatever they leave on the conveyor, smaller oysters, rocks and such, continues to the end and drops back into the water. Of course, the harvesting machine misses some 80-gram oysters. Those remain on the seabed, sometimes for years, growing larger. Like this guy, weighing about 1 kilogram. Prior to sale, the harvested oysters go through a cleaning process called depuration. For 42 hours, they sit in tanks filled with seawater sterilized by ultraviolet light. The oysters draw this clean water through their gills. This flushes out all the bacteria. Thanks to this depuration process, it's safe to eat raw oysters. It's taken a good 18 months to grow from microscopic organism to dining delicacy, which has a refrigerated shelf life of about a week. Long before satellites and Doppler radar, people relied on weathervanes for storm tracking. A folk art figure balanced on an axis turns with the wind to indicate both direction and speed. Though more ornamental than practical, it's still a great way to find out what's in the wind weather-wise. As it swings with prevailing winds, a weathervane offers important clues. Northeast winds, for example, could mean a storm is brewing. Learn to read the signs, and a weathervane offers up-to-the-minute weather information. To make a weathervane the old-fashioned way, a craftsman starts with a sheet of soft copper. It can be easily cut, bent, and shaped. Using electric shears, he slices the copper to the appropriate size. Then he clamps it to a steel mold of a rooster body and head. With a rubber mallet, he carefully pounds the copper into the crevices of the mold. This is a critical first shaping of the copper, and he has to hit it with just the right amount of force. If he's too heavy-handed, he could break or tear the copper. Too little force, and the shape won't properly transfer to the metal. With the basic rooster shape now established, he reaches for an air hammer that's equipped with a plastic tip. It beats the copper into the mold thousands of times per minute. This transfers finer details, like feathers. And with its smooth plastic tip, the air hammer inflicts no damage. It takes less than 20 minutes, and the rooster comes to life in copper. He unlocks the clamps and removes the molded copper rooster. He'll make another one just like it for the other side of the weathervane. This will distribute its weight correctly and make it look good from all angles. He then pounds copper into the shape of the rooster's tail. It has generous plumage for just the right balance. With the bandsaw, he slices around the molded shapes to remove the excess copper. This liberates the molded rooster from the matrix. He now trims the rooster with a set of clippers to give it a cleaner edge. Using longer clippers, he snips copper from inside the beak. This opens it up. Once the ragged bits have been trimmed, he's ready to match the two sides of this Weathervane rooster. He secures it in a vise and cleans the seam with a solution called flux. He tacks it with solder and then checks the evenness of the seam. When the two molds match perfectly, he solders the entire seam. This weather rooster is now ready for its tail. It will give the Weathervane a larger surface on one side, offering greater resistance to the wind. This will cause the front of the Weathervane to point into the wind. He inserts the Weathervane axis through the rooster's foot into the cavity, and it emerges from the back of the neck. He pounds the top of the shaft flush to the surface, and then solders it in place for a permanent installation. For some extra pizzazz, he slides a decorative copper ball up the turning rod, resting it just below the rooster foot. He secures it with solder. He now cuts out the feathered end for an arrow. It's known as the fletching, and it will help balance the Weathervane. He turns the crank of a press to roll numerous creases into the fletching. The creases mimic feather lines. He solders the feathered end to the pointed shaft. It has a hole for installing it onto the Weathervane's turning rod. As the Weathervane spins with the prevailing wind, the arrow will point in its direction. A wattle below the beak and a comb atop his head, and this rooster is ready to rule the roof. Exposure to the elements will weather the copper and give it a blue-green patina. For customers who don't want to wait a few years for this to happen, instant results can be achieved by applying a special acid. Depending on its complexity, a copper Weathervane can take up to 2 days to build. With luck, it could last a century or more. Like the weather, predicting a Weathervane's long-term viability is not an exact science.